absolutely nothing I can do for you. Okay? Other than to tell you that you're going to need to watch YouTube and catch up. Because I cannot duplicate what you're missing in class after school. There's no way I can go back and do an hour's worth of notes and teach that content. So you're going to need to watch that and catch up. All right, so we need to go. Let's see where that puts us. I think that's pretty close. All right, that's where we were on Friday, right? So we talked about what the photoelectric was on Friday. We said that it was the emission of electrons from a metal, correct? Now, we said basically that the dual wave particle nature of light explains that electrons can behave as light, correct? Now, that is very bizarre to scientists at this point in history. Electrons do not behave as waves. They behave as particles. So, there are two things we're going to look at today. Most of this stuff is incredibly odd, but unfortunately it's part of the curriculum. Why they put this back in the curriculum, I will never for the life of me understand. However they did, which is why I'm teaching it. Otherwise, I would never teach this stuff because it is just weird. Now, tomorrow's stuff, even though it's weird, I actually like to teach. So, wave theory said, according to the photoelectric effect, we should be able to use plain old fluorescent light bulbs. We should be able to take these fluorescent light bulbs, shine light on a metal, like aluminum foil, lay it on your desk, and when that light strikes the aluminum foil, an electron should come off. Does that work? Would you think so, or would you think no?
No.
No. Most people are bright enough intuitively to say, no, it does not work that way. Scientists were bright enough to say, that seems odd. So, but according to wave theory, it should work that way. So there has to be something else going on. So the whole conversation we're about to have for about the next 20 to 30 minutes explains scientists coming up with a way to explain why this happens when wave theory says it shouldn't. So what's going on? All right. However, only light above a certain frequency will knock electrons loose, which makes sense from a scientific standpoint. But according to wave theory, any light should knock electrons loose. So there has to be some other explanation as to why electrons are able to be knocked loose at only a certain frequency. So there's two scientists that we're going to talk about today that explain why only certain frequencies work. Okay, the first one is German physicist Max Planck. Now, Max Planck proposed that electromagnetic energy is not released continuously, but in small packets called quanta. And you're going to see me draw really weird pictures today to illustrate this. So, if you think about the way I drew this picture a second ago, I drew a straight line for light, right? Representing continuous energy. But starting now, instead of drawing them in straight lines, I'm going to draw my pictures as dots, because instead of them being continuous energy, Max Planck is proposing that these are small bursts of energy instead of continuous energy. Okay? Now, again, this was a theory at the time. Now, those bursts, he gave names called what? That's right. All right, those are bursts called quanta. And quanta is just plural. That's singular. The only difference. Now, a quantum is a minimum amount of energy that can be lost or gained by an atom. So those little bursts that I'm drawing up there have energy. And I have to possess a minimum amount of energy that can be lost or gained by an atom. I can't fix that. I know you. All right, we caught up? All right, you there now? All right. So, this minimum energy is required to eject an electron. Okay? If you don't have this minimum this minimum energy, can we eject an electron? No. So remember, all of this is about the photoelectric effect. For those of you who forgot what it is again, we're talking about the energy to get an electron to be ejected from a metal. So we're shining light on a metal and trying to eject an electron. So, Planck also said there's a relationship between the energy needed and the frequency. Okay? That there's a relationship between the energy of the light and the frequency of the light. Any guesses as to what that is? You think they're inversely proportional or directly proportional? These are going to be directly proportional. Okay? There's a relationship between energy and frequency. Now, this is an equation. I will tell you now, you do not have to know the equation other than to know the relationship. E stands for what? It's a universal symbol for what? Energy. V, we've already talked about. What's V? What's that? Frequency. E and frequency are the two you have to know. I only put this here because this is what H stands for. H is Planck's constant. You are never going to have to know this number. You are never going to have to know H. However, because I'm a science teacher and I don't leave blank spots in equations, I put it up there so you know what it is. But you are never going to have to tell me what Planck's constant is. You're never going to have to tell me H is Planck's constant. So if you don't want to write it down, you do not have to. Okay? But I'm not leaving blank spots in equations and telling you don't have to know that variable. So if you want to notate out to the side, you don't need to know that, feel free. Because you are not going to have to know what H is. You're not going to calculate with this equation. The only calculation we're doing is the one you did on the quiz today. Now, how are E and V related to each other? What did we just say? They're directly proportional. Now, do you remember from Friday what we said that meant? Yep. Is everybody caught up with me? No. Because I'm pretty sure I have that on the next slide. All right, so energy and frequency are what? They're directly proportional. And that means if one increases, the other increases. So if the frequency of light is high, then the energy will be high. Are we there? I wrote this one with you.
You didn't know she was gonna write.
How about now? All right, so.
You wanna write the top part, the outline.
Yeah. I'll tell you when you don't have to write. There's a part that you don't have to write. These parts you gotta have. Now, the next piece that was added by Albert Einstein. Now, Einstein explained the photoelectric effect by proposing that light can be viewed as a stream of particles. Now, this stream of particles carries a quantum of energy. Now, we're going to give this stream a name in a minute. Okay, so that's why I said I'm going to draw it with dots. So again, you've got this stream of particles. So again, it's not continuous according to Max Planck. Okay, and each particle has a what of energy? Each particle has a quantum of energy. And I know this sounds bizarre, and I'm going to go back after we finish writing and talk about it again. And I really wish we had Brain Pop still, but we can't afford it. It used to be really cheap when we first got it for the school, but now it's priced itself out and we can't afford it. Because it used to do a nice job with this topic, and particularly with electricity, and I could illustrate this nicely. So Albert Einstein said that the photoelectric effect is a stream of particles. It's not continuous. Okay? So you've got one particle and a break, another particle and a break, another particle and a break. Now each of those individual particles, though, carries a certain amount of energy. Now, does every type of light carry the same amount of energy? No. So microwaves, for example, don't carry the same amount of energy as visible light. Okay? Different types of BMR are going to carry different types or different amounts of energy. Am I giving everybody enough time? Yes? No? Okay. Got it. All right. Einstein called each particle of electromagnetic radiation. You do not have to know this part about having zero rest mass. Let me get rid of that. Okay. Called each particle that carries a quantum of energy a photon. So, let's just say this is light. And here's our stream of particles coming at the metal. each of these particles is a photon. Okay? And it carries a quantum of energy. So when I draw light, notice, first of all, that I've drawn light as particles. Light generally is viewed as a wave, but Einstein is saying that light, A, can be viewed as particles. B, it's not continuous, so I didn't draw it in a straight line. I drew it in a broken line to illustrate that it's like he suggested. And each of those individual particles carries a certain amount of energy. Like we just said, depending on the type of EMR, it has a different amount of energy. So they have to carry a minimum amount of energy. Now, the type of metal dictates the amount of energy it has to have. And we'll come back and review all of that in just a second. Just trying to get the notes down, and then I'll come back and review it. Is everybody caught up, or do I need to wait? I see a few people writing. All right, got it? Nope. All right. Now, the energy of a photon, how much energy it has depends on what? What does this energy of a photon depend on? It depends on frequency. Now, this is what we talked about earlier with the equation based on Planck. Okay? Energy depends on frequency. Energy of that photon. Okay? So if I go back just one slide for a second. Okay? The energy of these photons that I'm talking about right here, the energy these have, depend on the what? The frequency of the radiation. You know those calculations we just did on Friday that you had a quiz on today? The frequency determines the what? Determines the energy. If you have low frequency, you have low what? Energy. Are you going to have enough energy to eject the electron? No, probably not. Okay? So the higher the frequency, the higher the energy. You have to have enough energy to eject the electron. Aren't you glad we got out of the math?
No, I'm taking notes.
No, yeah, I'm gonna do it now.
I don't really do that.
Okay. Everybody got it?
Hold up.
I see Jade's still writing.
Stay. Stay on your desk.
That's something we're going to use in a minute for neon lights. All right. Last slide for the photoelectric effect before we do neon lights. But I need to go back and explain to make sure everybody's with me. So, This is just in summary. So you can choose whether you want to write this one or not. Okay? Now, but it's a nice summation slide of everything you just wrote. So, in order for an electron to be ejected, what do you have to have? Okay? The metal in the electron must be hit by a what? You have to have a what? In order for an electron to be ejected, you have to have a single photon. And it has to have a what? A minimum energy. What's another name for that minimum energy? A quantum. Okay? It's required to knock it loose. Now, that minimum quantum of energy, you could also say, has to have a high frequency. Okay? Because a high frequency equals that high energy. Okay? You can't have a quantum if you don't have a high energy. Does that make sense? Okay. If you understand what I just said, then you understand what we just went through. If you have no idea what I just said, then you've no idea what you just wrote down. All right, so the last thing I have up here is what happens for different metals. Do they all work the same way, or are they different? Okay, so different metals, are they going to require the same amount of energy? No. So if different metals require different amount of energy, will their quantums be the same? No. So that's what the brown color sort of says. Different metals bond differently. They will require different energies. Their quantums will vary for every different metal. They're not going to require the same quantum of energy. They're not going to require the same frequency. Okay? Does that make sense? Other than it's just weird, does it make sense? Based on what we talked about. For the 5 people who are with me. Okay. I'm going to go back through it with the slides for those of you who are looking at me like I have 3 heads. Neon lights are a little easier to understand. And there's a lot less writing. All right, so everybody caught up so I can go back and review for the people who are not with me. You said wait, Jay? Yeah. Okay. All right. So if we cruise back, make sure we've got most people with us. All right. So we said for those people who don't remember, the photoelectric effect is about getting an electron out of a metal. What has to hit the metal in order for an electron to come out of the metal?
Photon.
Light. Okay, let's start easy. Light has to hit the metal. Now, will any kind of light cause an electron to leave the metal? No. A certain kind of light has to hit the metal. So, what kind of light has to hit the metal? Well, Planck said when he did this that he suggested a certain kind of light. This light can't be continuous. The light has to hit the metal in what? Quanta or packets, all right, or bursts of light. Does that make sense? Karen, can you see anything up here? Do you have your glasses today? Do you want to sit closer, or are you just going to keep taking pictures and squinting? Okay. I say you can sit in front of Jade if it will help, or you can sit up here at the counter and move the stool up at the computer if it will make life easier for you. Okay. So, he said this quanta, or quantum, which is singular, is a minimum amount of energy, right? Now, in order for this electron to be ejected from this piece of metal or aluminum foil, that burst of energy has to be high enough for it to be ejected. It has to have some minimum amount. Does that part make sense? Okay. Now, we did that. Planck also proposed that there has to be a relationship between energy and frequency. You only have to understand the E and the V. You don't need to know H. Is everybody with me on that part? If you wrote it down, fabulous. Make a note in your notes. You don't have to know H. Okay? You only have to know E and V. You don't need to know the H. Okay? I just can't not put that stuff up there. Okay? So, how are energy and frequency related to each other? They're directly proportional. So if you have high energy, so here, if this is a high, whoops, wrong way, genius. If this is a high energy light, that means what? It has high what? Frequency. You have a better chance of this electron coming off. Okay? Does that make sense? If it's low energy light, it is less likely to emit the electron. So, then Einstein pops onto the scene, and he says there's a stream of particles. Okay? This stream of particles is called a what? Okay? Each particle is called a photon. Now, these photons have to have a quantum of energy. Now, this quantum of energy, okay, this quantum of energy, again, has to have a certain what? What color am I? Green. Has to have a certain frequency. If we have a high frequency, that means we have high energy. If our energy is high enough, we have a high enough frequency, the electron will be ejected. If we don't have a high enough frequency or high enough energy, is the electron going to be ejected? No. So these plain old fluorescent light bulbs, do they have a high enough energy and a high enough frequency to eject an electron from our aluminum foil? No. That's why we can leave the aluminum foil sitting on this desk all day long. Nothing's going to happen to it. It's not a powerful enough light. Now, what do I have there? We just did that. And we did that. Okay? Now, we have all kinds of metals. We have copper, we have tin, we have zinc, we have gold. All of those metals are bonded differently. They're going to require a different amount of energy for those electrons to be loosened from the metal and to be ejected. Does that make sense? Yes? No? Okay. I'm going to trust you that you're with me. All right, so now we're going to talk about neon lights. Everybody's seen them. Beer coolers, bars, restaurants, open signs, closed signs. If you've gone to a dry cleaner, you've seen neon lights. Okay? Well, pay attention next time you go down Main Street. There are plenty of them. Now, we need to talk about how neon lights work. we need to talk about the ground state and the excited state. Now, my neon light looks a little bizarre because the neon light that I'm using fits in this lovely box that Xavier just asked me about. Now, my neon light is shaped like that neon light. It's a glass tube. It's got crap on top of my neon lights. I need y'all's openings and y'all Mr. Quiz.
Yeah, I figured.
All right, so my neon light looks like that. Now, at the moment, my neon light is in what's called ground state. The ground state is a state of lowest energy. Now, in a minute, I'm going to turn on this lovely box, and I'm going to pass a high voltage current through those electrons. Now, they're going to go to the excited state. And it's going to become a state of higher energy. Now, notice the ending I used. I said I didn't say ist. I said state of higher energy. Now, if it becomes highest, then I'm going to mark it wrong if it's on the quiz tomorrow. It's the state of higher energy. There are multiple levels of higher energy. It's not an ist kind of thing. Now, if you look at the back of your blue sheet, you see where you have this lovely Bohr model? You got this little black dot which represents the nucleus, right? If you leave N1 and you go to N equals 2, that's a state of higher energy. How many states are above N equals 2? 4. All of those are above. Those are all higher states, okay? So just because you went to 2 doesn't mean that's the only place you can go. Any of those above 2 are higher states, okay? So we're going to go from the ground state to the excited state. Now, when I get to the excited state, do my electrons stay there? No, they go where? They go back down. Okay? When they go back down, what are they going to do when they go back down? They're going to go back up. But before they go back up, what are they going to give off? Remember, this gas is all contained in the tube. Unless I accidentally drop it on the floor or somebody broke it between. Yes, but what kind of energy? They're going to give off light. Okay? Now, because I'm using a type that you can see, you're going to see visible light. Now, does it always have to be visible light, though? No. So this could be any type of EMR. All right? But if I picked any other kind of EMR, some of y'all would be like, Tomas, that's well, how you know that's actually giving off that? And I'd be like, I don't know. They said it was. All right? So I picked something that when Tomas or Andy asked me that question, I could go, because I could see it. All right? So I picked something this time that I knew was there. Okay? So at the moment, they're in what state? They're in the ground state because there's no electrical current passing through. It's not too hot yet. I can hold it. All right? Ooh, it's getting a little warm. So you see these metal tips here and here? Okay? They are metal tips inside these plastic pieces. And so when I put this back in here, all right, this is going to pass a high voltage current through here. All right? It's called completing the circuit for those of you who know anything about electricity. So when I turn this on, these electrons are in the ground state. they're not going to stay in the ground state. They're going to continuously loop between the two. So any neon sign that you see any place in town, maybe you have some at your house, they continuously loop between the ground state and the excited state. So those electrons do this automatically. We don't control that. So they go from the ground state to the excited state. Now, when they go from the ground to the excited state, they absorb energy. And when they come down, they emit energy or emit light. Okay, those are two words that you may or may not know from another science class. Now, this is a continuous cycle. It loops so fast we can't see it. Now, if we could slow it down, you would see again, just like with the photoelectric effect, that there are bursts, okay? That it happens and there's a break. It happens and there's a break. But it happens so quickly, we can't see that. Now, again, if we had brain pop, I could illustrate it, but I can't do it because I don't have access to it. So, I was getting ready to say something, but it's gone. It's horrible to get old. I'm going to. Oh, well, it's just gone. So this one that I'm using at the moment is hydrogen, okay? So the one I've picked to illustrate with is a hydrogen light. Everybody got what they need off this slide? Because I'm going to change that in a minute and show you something else.
What's that noise?
It's the hum of the electricity flowing through that thing, which is one reason it gets so hot. All right, does everybody have what they need? Okay. Now, we did that. All right. So, give everybody one of these.
What the? It's a rainbow.
All right. Now, you guys have all seen this before, so this should not be earth-shattering to y'all. Now, in earlier science classes, y'all have had light pass through a prism. Y'all can look through the narrow end. You pointed at the lights, works better. Okay? Look through the narrow end, point the wide end to the lights. What happens when you look through a prism? What do you see?
I don't see nothing.
Okay, you don't see nothing. We got problems.
You shine up at the light and look.
Oh.
Did I say that?
Yeah, but I just that.
Hey, cool.
What do y'all see?
Light, some colors.
Some numbers.
All right, I got some numbers. I heard the rainbow. At least I'm getting somewhere. Okay. The rainbow is the most untechnical answer y'all can give me. We need to spruce up the rainbow here, because rainbow is not an answer I will ever take. What? I can live with that. That's getting a whole lot closer to what I want. Okay? Visible light is the answer I can live with. Okay? Visible light, visible spectrum is what I was hoping for. Okay? Visible light or the visible spectrum is what I want. Now, for those of you who don't know, okay, so that answered the question. What do you see when light passes through a prism? You see visible light or the visible spectrum. For those of you who do not know the order of the colors, someone should have taught you Roy G. Bibb.
Yes.
Okay, I'm always amazed at the number of people who have never heard that. All right, Roy G. Bibb stands for the order of the colors in the spectrum. Thank you, dear. All right, red, orange, yellow, blue, indigo, and violet. Indigo is a really dark blue. Now, what determines the color that we see? Why do we see red? Why do we see blue? Why do we see green? Frequency. Close, very close. Flip it.
Energy.
Wavelength. Okay? The color that we see is determined by wavelength. Now, if you listen to, I think it was Samaria a minute ago, I can't swear to it, but I think it was her voice, who yelled, "I see numbers." Okay? Those numbers match up to the numbers on the blue sheet. Okay? So if you look at your numbers on your blue sheet, where roughly the 4.0 is on the sheet, that lines up with roughly the 4 in the spectroscope. Now, mind you, these things only cost like $3. These are not the most technically sound pieces of equipment we own. All right, so they're not going to be all that accurate. They should. Oh, you got that.
Yeah, 6 is pink.
Okay. However, the 7 should be somewhere, hopefully, around the red. The 4 should be somewhere around hopefully, the violet. Okay? The 5, the 4, those might be a little skewed.
4 is black to me.
Some people can't even see the colors. Okay? I guess I should be thrilled that you see 4 black.
Colorblind.
Okay? Now, but the numbers line up with the wavelengths, roughly. Okay? Roughly. Everybody with me on that?
Yeah.
Okay. Now, what happens if we take that same thing you have in your hand and we look at this? What do we see? You can do it. You're still going to see the visible spectrum because of all the visible light we have in the room. We'd have to be in a completely dark room for this to work. Okay?
All right.
What you see, Daddy?
It's the same.
We're going to see the same thing, people. We have blinds we can close. We still have light over here.
You cover it with a curtain.
Still not going to work all that well. All right? Because there's too much visible light in the room. Now, are we going to see, okay, what would we see? This time, we would get what's called a line spectrum.
I didn't see nothing.
You're not going to see anything. Now, you see these lovely line spectrums that are right here on this door?
Yeah.
This is what you would see. Mostly, it would be what you got the last time when your lamp was well. All I see is black. Okay? You're supposed to get for hydrogen mostly black. There's 2 tiny little blue lines. Okay? You'd get a blue, and then there's 2 more. There's a really sort of pale bluish green, and then red. Okay? That would be what we'd see if we looked at hydrogen. The rest of it, all in between, would be what? It'd be black. Okay? But that's what you would see if we had a pitch dark room that we could use. Normally, I would let people use the stock room and we would do this, but with the remodel, they took every electrical outlet out of the stock room. It's not an electrical outlet to be found.
You got an extension cord?
No, I don't. That's why I keep unplugging everything under the desk. Okay?
You can go get one.
I probably should, but I haven't. All right. So,
If I bring you one, can I get extra credit?
no. What determines the color we see? Here. What determines that we're going to get 2 like blue lines, a really light yellow or blue greeny, and a red line? Wavelength. Okay? It doesn't matter whether we're talking about the visible spectrum or whether we're talking about one of these weird looking lights. Wavelength always determines the color that we see. Now, those of you who've taken art class and you've learned about colors that are absorbed and reflected, that's still all very valid. But the colors are still determined by wavelength. All right, does everybody have what they want off this?
No.
Hurry up.
You go. Stay.
I don't care who stinks. Stop.
Shut up.
Should care who stinks.
Shut up. Shut up.
Yeah, so you don't choke out.
All you gotta do is be quiet. Okay, fight.
All right, you got
We're
it?
gonna beat you up.
That's a lot. Yeah.
All right. So,
What y'all doing? Good smell.
All right, so what color was that hydrogen one so I can write it down? The one I just took out.
Pink.
All right. So hydrogen was pink.
You
All right, this one is, what did I just put in here? Argon.
Argon. Ooh.
All right, what's argon?
Light, very light blue.
Light blue.
Pale blue.
All right, so light blue. All right, so we got light blue. Nitrogen.
It's orange, peach color.
All right, so peach. And unfortunately, neon I broke 2 years ago, so I can't show you true neon. But I'll tell you what it is in a second. That one is water vapor. That one's water.
It's the same. It looked the same.
Okay. All right. Neon is bright red. Okay. So the true red signs you see are true neon. All right. So tell me this. Why do they have different colors? Okay. Different wavelengths. All right. Why do they have different wavelengths? Okay. So why do different elements have different colors of light and different line spectrums? Okay, you gave me different wavelengths and frequencies. So why do they have different wavelengths and different frequencies? Okay, so we have different numbers of electrons, and there's one more piece. The numbers of electrons are different, and one other thing. This is where we're going over the next roughly week. Week and a half.
Protons.
Protons are the nucleus. It can't do anything. It's got to do with the electrons. The number of electrons are different, and something about the electrons. What? Now their color.
It's something we already talked about. What it start with?
Sort of.
Is it a metal? It has to do with a metal.
I'm not gonna measure it.
Length. Right. Low.
Low. Locomotive.
Local.
Location.
Oh.
And the location of the electrons. All right. Now, because the location of the electrons is going to vary, their properties are going to be different. Okay. Now, some of you may have learned, maybe in middle school, about the Bohr model and learned about the rings. Some of you may have even learned the rules for figuring out how many electrons were on each ring. Some of you may have, not everyone. Okay. If you learn that, we're going to talk about how you figure out how many electrons are on a ring and where those rules come from. We're going to learn about the energy levels, the sublevels, the orbitals, how they spin. You're going to learn more about electrons than you ever wanted to know, which is why I said the next 2 days, for those people who are going to be out, are really going to have to watch the YouTube stuff, because I can't redo that for y'all. Because I can't. Not only can't I just won't. Now, Bohr's model. For those of you who had a fairly decent background in middle school,
No, you know that.
I've got people in third period. Some people in third period actually told me they had this in middle school. They remember doing it. They built a model. Other than Baden. I've got like 6 people in third period who keep telling me they did
They
this.
lied to you. Don't let them lie. Don't let
They were on the
them lie
other
to
side
you.
of the hallway? Okay. Well, they were on the other side. Okay. Anyways, if you talked about a Bohr model, you may have actually built a model. Okay? If you didn't, okay, you should have built a Bohr model. So, let's talk about it. So, let's just say that we have sodium. Okay? A sodium atom has how many protons? This is review for those of you who forgot. Yeah. 11 what? 11 protons. Okay. How many electrons?
11.
All right. And let's just say for the sake of argument that its atomic mass is 23. So how many neutrons are we going to have? I was hoping for more than that one person who yelled out an answer a minute ago. At least that's a few more people. How do we find neutrons again since so few people were saying anything?
You subtract the atomic number.
Do we need to draw the little circle thing?
Oh, I'm going to explain a couple things. So that's up to you. Okay, so 23 minus the 11 is how we got 12. Now, tell me what you know about the atom from earlier in the semester. What goes where?
The protons and the neutrons.
Okay, so here in the center in the nucleus, right in there, okay, and this big green dot, we know that we would have the protons and the neutrons, right? Okay, so out here on these rings would be our electrons. And in middle school, you should have learned. It's okay if you did. You should have learned that on the first ring, there are 2 electrons. So you would have drawn or built a model that had 2 electrons on the first ring. On the second ring, you should have learned that there are 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Now, how many electrons have we put in this model so far?
10.
2 plus 8 is 10 in my world. Okay? Just saying. Okay, so 2 plus 8 is 10. So how many more do I need to put in?
1.
Just 1. So I'm going to put it where?
The last ring.
On the last ring. Okay? Now, that means there's how many electrons on the last ring? 1. We refer to this as the outer shell, which we'll talk about down the road. Okay? Now, all of that you should have at some point in time done in the middle school. But if you didn't, completely okay. Now, in a Bohr model, okay, we generally refer to this sometimes as the planetary model. Okay? A lot of people will refer to this as the planetary model. Because the nucleus sort of looks like the sun, and the electrons sort of look like the planets, and they sort of roam around the sun. Okay? Now, the thing about Bohr's model is those electrons have to be on the what? They have to be on the rings. Okay? And in modern quantum theory, that piece is actually wrong. Okay? So even though we teach Bohr's model in class, it's not actually right. Okay? So, I know Tomas is either making faces at Andy again, or he's like, why are we teaching stuff that's not right? Why are we teaching stuff that's wrong? Because it's an easy way to give people an intro to, yeah. I know. We teach stuff all the time that way. It's okay. So, Bohr's theory. What do you need, dear?
I'm just writing.
Bohr's.
All right, so Bohr's theory has 3 parts. Okay? The three parts to Bohr's theory are, first of all, electrons circle the nucleus in those fixed energy ranges. They're called orbits. Okay, those rings are called orbits.
I think I remember.
Okay? Now, this part is not correct. Okay? The orbits part, not right. It's been updated by a guy named Schrodinger that we'll talk about tomorrow. That piece is not correct.
This went for chemistry class. I wrote that down for nothing.
No, you still need to know it. I wouldn't be teaching it if you didn't need to know it.
Some teachers do.
Bohr's model is part of your curriculum. You have to know it, even though he's got parts that are wrong. All right? An electron could only move up and down between the orbits. Sort of like, we describe him as like a ladder. You know how when you climb a ladder, you have to stand on the rungs? You can't hover between the rungs. You have to stand on the metal rungs. Same thing here. Okay? The electrons have to be on the rings. They cannot be any place else but on the rings. So if they move between one ring, they have to go to the next ring. They can go from one ring to another ring. Can they be between the rings? According to Bohr, no. Okay? So number 2 is not right either. Okay? Huh? Because you do. Now, number 3, he has correct. Okay? So the electrons closest to the nucleus are lowest in energy. So if you look at a model that has like 2 rings, and you have an electron that has 3 rings, all right, which one would have more energy? The one that has the electron on the 2nd ring or the one that has the electron on the 3rd ring? That's right. The one that has the 3rd ring would have more energy. More energy would be on the 3rd ring, okay? Because the electron closest to the nucleus is lower in energy. So that 3rd ring is going to be higher in energy. Does that make sense? But he has that piece right. Okay? Now, the reason you have to know Bohr is he's the precursor into Schrodinger, which we're going to do tomorrow. And Schrodinger is not hard. Now, the only thing we didn't get to that we need to just hit the highlight of in a few moments, because it's not hard, and y'all are sharp people, is reading a chart. Okay? Everybody got their blue charts on the back page?
Yeah.
You already have your homework. It's in your hands. So turn to the back page. Turn to this. Suppose I want you to tell me the color of light from, not form, from n equals 6 to n equals 2. All right, how do we do that? N equals 6 to n equals 2. All right, here's your n equals 6 right here. Here's your n equals 2. Okay, find your dot that's on the n equals 6 ring. It goes to the n equals 2 ring. Find that line. We got it? What number is it? All right, so Mario's with me. Jonathan's nodding at me. I got 2 out of 19 people.
Yeah.
You got to be able to do it tomorrow on the quiz. Okay? It's on it. All right, so follow it down. You got 410. That's 4.10. So when you look on your sheet, where does 4.10 fall for color? There you go. There's your color. Questions about how to read the chart. Now, if you look on the back side of your homework sheet, or really the front and the back side, you are able to do the rest of your homework sheet from last night. The only question you cannot do is question number 21, because I never do the Bohr model. Okay? The only one you can't do is 21, because it said, given the following Bohr model, I never drew the Bohr model.
So we're doing it on the back.
So you're doing everything. 12 through, or 13, 12, whatever the last, we did what, 1 to 11?
I'm busy.
All right, so if you will, when you turn in your calculator, give me my spectroscopes. Calculators and spectroscopes. I'll leave that there. Put your calculators up and your spectroscopes up.